Hello, everyone. Welcome to our second part of Julia for Engineers series. So what I thought we'd do today is cover, let me go ahead and get this set up correctly, cover a problem that I've actually experienced before in the past that I solved using my favorite tool, which is modeling. And to explain first, to take a step back and just explain if you've heard the term JuliaSim before and how that relates to Julia and the tools that we'll be using today, there's this schematic here to kind of explain the whole story. So JuliaSim is a set of tools for building and using models. And it's a full collection of tools. And so each of these boxes here represent a subsection of all those tools. And as you go from left to right, you'll see kind of the story of a typical engineer's life. So if you're using models to solve problems, the first step in that story is going to be that you're going to need to actually develop a model. And so JuliaSim provides that model development tools. There's both a visual drag and drop tool that'll be coming soon. And there's also the ability to work with those models in IDE, so Visual Studio Code, for example, VS Code. Once you have that model, you probably want to be able to refine it. So that's part of our JuliaSim AI tools, being able to bring data into your models, make them calibrated more closely to real life data, and being able to do really cool things like discover actual physics. And once you have a model that is now very accurate, if everything is going according to plan, you can then use that model to do some very important work, such as design, being able to optimize or calibrate the parameters, and also being able to design controllers and create surrogates of the model so you can have some very, very fast run times. And finally, once you have all of that done, you probably want to be able to deploy that model somewhere, share it with a team, or work alongside a team. So that's where now JuliaHub comes into play. So you can be able to easily deploy your models to JuliaHub, or be able to generate FMUs so you can share it outside of JuliaHub. And we also have some nice tools for being able to integrate with your CI/CD process. Okay, so as you can see, this is the JuliaSim story. It's a set of tools that sit on top of what is the open source tools that exist in the SciML ecosystem. And then, of course, all of this is made possible because of Julia itself. And so what we're going to be talking about today is what lives inside the SciML ecosystem, which is Modeling Toolkit and differential equations. So those are your two kind of core tools that enable all of this that I just described. Okay, so enough of the sales pitch. Let's go ahead and get into the workshop and getting some actual work done using Modeling Toolkit. So this is our key tool for being able to build and solve models. And so what I'm going to talk to you about today is actually a problem that I solved previously. If you've seen a previous workshop that I hosted back in December last year, I discussed a hydraulic safety problem. So I'm going to actually go over that same problem again today. However, that was done back in December, and we're now several months past, and Modeling Toolkit is evolving extremely quickly. And therefore, a lot of the things I said back in December are no longer true. And we actually have some enhancements and some improvements that I can describe of how what I did back in December can actually be made better now. So if you watched that before, it's not going to be just a repeat of exactly what I said before. It's actually going to be showing you how to do it again, but much better. And if this is the first time you've seen me give a webinar, I'll be going through all the details and it'll also be useful if this is the first time you've seen it. So that's what we're going to go over first. Is I'll tell you what the problem is, what we're trying to do. We'll start with just doing some math, figure out what exactly is the problem, how we're going to attack this problem mathematically. That's the part where we're actually building the model, of course, or at least on paper, right? What should the model be? What are the variables? What are the equations? And then we're going to solve the problem in three different ways. We're going to solve it without time being involved. So we're going to do the most basic approximate solution to the problem. Then we're going to go one level deeper in fidelity and introduce time. But we're going to keep the problem still in a simplistic manner. And then we're going to add one additional level of fidelity and make the problem compressible. So we're doing a hydraulic problem. So if we do incompressible, equations are easier. And then if we move it to a compressible problem, then it gets much more challenging. So we're going to go through all three levels of fidelity there. The code that I'm going to be covering, I've posted here in my GitHub under Julia for Engineers. So hopefully you can find that easily. And you can go ahead and clone that code if you'd like, so that you can easily copy paste the code that I'll be running. But you don't need to do that. You can also just follow along. We're going to go line by line here through all the code that I build. Okay, so here's the problem. Actually, let me pause here for a second. And also just to mention, I'll try to pause as I go through this webinar and take a look at what open questions we have and try to address them live. So don't hesitate to go ahead and post any questions or raise your hand if you'd like me to dwell on something a little bit longer. Okay, so let's see. So there's a question about complex vectors in Modeling Toolkit. There is a support for vectors and arrays in Modeling Toolkit. We won't cover that here, but I think that actually might be a great idea for a next part of the series. And then when you use the word complex, if you're referring to using complex numbers, that's actually a very good question. And I think I'm going to need to get back to you on that one. I've never done a model with complex numbers before, so I'm not sure that that's supported. There's one more question about PDEs. Yes, Modeling Toolkit does support PDEs, and I'll try to address that a little bit higher level when we get into that. Okay, so yes, so here is the problem that we're trying to solve. What you see here on the right is a hydraulic actuator. You can imagine that this is a machine that would be a hydraulic press. So it's simply going to bring pressure into the top chamber and pressure out of the bottom chamber, move this actuator down, and potentially this is going to be used to squish some metal, right? And the way that this machine would work is that these two ports, PS and PR, would be connected to a valve and a controller and a pump. So the pressure is going to be coming from some kind of pump source, and then there's going to be a valve that's going to be able to direct pressure in this way and take pressure out of this port. So we're not going to include all of that in the system. The problem that we're going to try to solve is exactly what happens when that system fails. So if you have a valve and a controller, and maybe the controller is one of the wires gets disconnected, for example, and the controller is no longer live and you have an open loop. And it fails in such a way that it's going to send a tremendous amount of pressure to the top chamber and remove all the pressure from the bottom chamber. That would be the worst case scenario if you happen to have your hand under this actuator. Because what's going to happen is this thing's going to slam down at maximum speed, probably faster than you can remove your hand from the machine. So what should we do to solve that problem? So we can make this machine safe. What we're going to do is we're going to introduce a couple sets of restrictions to ensure that if that does happen, that there's no way that this thing's going to be able to move too fast to be able to be a problem. So we can make it safe using some orifices that restrict the max flow of oil or hydraulic oil through the system. Okay, so we go ahead and do some research, and we find a distributor who sells exactly what we're looking for, an orifice plate that can restrict flow. And the manufacturer provides us this information that I'm showing here, which allows you to calculate exactly what size orifice we need. So essentially, we're going to have a plate here with a hole in it, right? And that hole is going to be some area A sub O. And that flow through that orifice is going to be dictated by this equation, which is simply that the pressure differential across that orifice is going to be equal to 1/2 rho, which is the density. U is the fluid velocity through that orifice hole, and then times the discharge coefficient, which is a coefficient provided to us by that manufacturer. They state that it's equal to 2.7. Okay. So we can determine what is that flow through that orifice is going to be a function of the flow rate we have through the whole system. So if Q represents the flow rate, then if we divide Q by this area, so this is in meters cubed per second and the area is in meters squared, you can see if you divide these numbers, then you're going to end up with a velocity, meters per second, right? That'll be the velocity of flow going through this orifice. And we also can see that the flow rate is going to be dictated by how fast this actuator is moving, because the area, this surface area of this actuator times its velocity will be exactly how much this volume is changing in time, right? So those are the things that we know here, okay? And what we want to do is assemble a system of equations so we can figure out what exactly would be the correct size for that orifice. So in order to do that, we also need to figure out what is the set of equations that define the actuator. So an actuator is really just a mass that has forces imposed on it. So we can use Newton's second law here to define how it behaves. Newton's second law is simply mass times acceleration. So that's x represents the position of the actuator. So x dot would be its velocity, and x double dot represents its acceleration. So that's the nomenclature that I'm using here. And as we know from Newton's second law, mass times acceleration equals sum of forces. So the sum of forces in this case are the force acting on the bottom area of the actuator, then there's the top area of the actuator, and this actuator might also be connected to a damper. So that's exactly what we're going to do in this case. So that's 3 forces. They're summed here, and there you go. That is our actuator equation. And finally, we can now assemble a set of equations. So we have now 4 equations to represent this. We have our orifice and pressure differential connected to the first chamber. We have the second chamber, same thing. We have our actuator force balance, and we have this information about what is the fluid velocity, right? So that's 4 equations. And if we look at what are the unknowns, what are the things that we need to solve here, we also happen to have 4. So that's what we're always trying to figure out as engineers, is trying to figure out what is our system of equations and unknowns that we're trying to solve. And whenever they balance, that's a good day, right? We finally have a problem we can solve. Okay, so in this case, what we're going to do to solve a steady state problem is we're going to ignore all the dynamics, and we're going to say we simply want to make sure that the actuator doesn't move any faster than 1 meter per second. So that is kind of our design specification, right? Our manager came to us and said, you know, I don't want this thing to move any faster than 1 meter per second. So that's exactly our target. So this is going to be now set as a constant. And everything else is what we need to solve. So we need to solve for what is the fluid velocity. Most importantly, what is the orifice area? This is the thing that we're trying to figure out that we want to purchase from a manufacturer. And we don't know exactly what the pressures are going to be to provide that fluid velocity. And if you count, you can see that we have 4 distinct unknowns here, and of course, 4 equations. Okay, so enough talking about the problem. Let's go ahead and move to Julia so we can actually solve that problem. And before I do that, I just want to make one more comment here, is that this problem, of course, could be solved easily by many different mathematical problems, right? There's many great tools for being able to solve a simple set of equations, right? So why would we want to use Julia? So what's fantastic about Julia and what sets it apart from all the other tools that you might go to and use is that Julia has the power of all those other tools. So it's going to be able to do symbolic math, but it's going to be doing that inside of a full-featured programming language, which means that you're not going to be limited to what you can do with Julia. So you can do with Julia what you can do with many other mathematical programs, but you can go much further than that. And so that's what I'm going to try to give you a little flavor of what that looks like. So let's go ahead and switch now, as I mentioned, to Julia. So before I go too far, let me go ahead and just check the questions. Let's see. Okay, no new questions. Very good. Hopefully everyone is following, and this all makes sense so far. So if you're new to Julia, let me just give you a couple pointers. As you can see, I'm going to be doing this work live or local on my computer. So in the previous series, Matt did the work on JuliaHub itself using a Pluto notebook. What I wanted to show here is how would you use Julia just locally on your computer, to do that, what is the highly recommended route to go is to use VS Code, because VS Code offers an extension which is simply called Julia, and that makes working with Julia extremely powerful. And I'll be going over those features as I talk here. The other thing that you want to pay close attention to when using Julia in a local installation is what is your environment. So this is probably one of the biggest learning curves for Julia, but also one of its most powerful features. So understanding how environments work in Julia is something that you really want to spend some time really understanding it very clearly. Because it's going to make your life a lot easier as you go. So what I've done here is I launched Julia. Actually, let me go ahead and just start from the very beginning. So I'll type Alt-Jo to launch Julia. And before I did that, I paid close attention to what it says down here. So this is that my environment is Julia for Engineers. That is telling me that it's looking at this folder that I'm in now, which is called Julia for Engineers. And it identified that there's a project.toml file. And that means that when I launch Julia, and if I go to package mode, which looks like this, and can be, you can get to package mode using the closed square bracket key. Okay, so if I hit backspace, that takes me back to Julia, square bracket, close square bracket, that goes back to the package mode. And this also shows exactly what I want to see, is that I'm in the Julia for Engineers environment. So if I look at the status of this, I can see that this is the software that I've installed in this environment. I'm using Modeling Toolkit. This is the latest version of Modeling Toolkit. I'm using Ordinary DiffyQ. This is the latest version, and I'm using plots. And so if you want to recreate this from scratch on your end, what you need to do is simply go to package mode, type activate and then dot, that means that you will be, if you didn't have a project.toml, that means you will now have begun one in the folder that you're working in. And then you can simply type add modeling toolkits, ordinary diffq, and plots. And then you'll end up with a project.toml that looks the same as what I have here, minus modeling toolkit standard library. I'm also added this in case we have a little bit of extra time. I can discuss one additional step we can take with how to build this model. Okay, so once you've done that, then you're all set, right? And you can be able to follow along with what I'm going to do here. All right, so after installing these packages, the first thing you want to do is use them. So normally I put at the top of my scripts what is the packages that I'm using. They don't have to go at the top. They can come at any point in time before you start using them. But this is typically what I like to do. And what I'm going to do here is I'm going to start with the code that I had gone over in the previous webinar. And I'm going to be talking about what changed from what I did last time and some changes that you can make now. So what I started with last time I did this webinar was I was using these three packages, and you might notice I'm using differential equations, but currently I've added ordinary diffq. So what I want to explain here is that ordinary differential equations, ordinary diffq.jl, is a subset of what exists in differential equations. And it contains, for the problems that we're going to be solving, all of the solvers that we need in a subset of DifferentialEquations.jl. And that was true when I spoke back in December. And we could have used ordinary diffq previously, but ordinary diffq just got a new feature, which is that it can now provide automatic solver, provide the solver automatic that you're trying to use. So you don't have to specify exactly what solver you want to use when you actually get to solving the problem. Previously, that feature only existed in differential equations. So why would you use this instead of just differential equations? Simply because this is a smaller package. There's less to precompile. There's less to download. It'll get you started a little bit faster. However, there's nothing wrong with using DifferentialEquations.jl. That'll also work just fine. Okay, so let me go ahead and get started by loading these three packages. I'm just going to highlight them and hit Shift-Enter. And that is a feature that you get when you're using the VS Code extension. So you now have this ability to interact with code, and the REPL are now linked together. So this is one of my favorite features that the extension offers you, being able to just do line-by-line execution of code with your and see what's happening in the REPL and with inline results. It's an extremely powerful thing. Okay, so let's go ahead and actually get to the part where we do some math. So as I said, we're trying to solve this steady state problem. And the equations that we were solving, I have written here. So I have the four equations that I was discussed before, and I have the variables, but I've made this a little bit different from what I put on the slide. If you have any variables that are defined on their own, so we had u as we were calling this a variable, this can actually be eliminated from your actual variable set that you're solving, because this is actually just a symbolic expression. So I'll show you what that means here in a second. So first, let's start with from the very top. So any modeling that you're going to do is going to involve parameters, and it's going to involve variables. And so what Modeling Toolkit gives us is two keywords or macros that we can use to help easily generate those parameters and variables. So we can write at parameters and then list all of the parameters with their default values like this, and they can all be collected in this one array called pars. So if I execute that, you can see down here we have pars, and it shows a vector of a type num, which means a symbolic representation. So you can see we didn't get a vector of numbers here. We got a vector of symbols. So if I type A here, it shows me that's just A. It's just a symbol. If I say 2 times A, I just get that symbolic expression, right? I'm not getting actual values. They're not going to be actually computed until we go to solve something, right? So we'll see that next. Okay, so now we can define a set of variables. It looks exactly the same. We collect that in a array called bars. Okay, so as I said, I removed one of the variables that I showed on the slide here as a symbolic expression. So when I evaluate this, you can see that's what I get. I get a symbolic expression. And so when I type u here in the equations, it's just going to substitute this symbolic expression into the symbolic equation that I've written. Okay, so if we evaluate this now, and you have a look, you can see that's exactly what happened. U is now being simply substituted in as a symbolic expression. Okay, and so as was covered in the last part of the series, to define equations, we need to use this tilde operator instead of an equal sign. That's one thing you want to just pay very close attention to. It's a definite modeling toolkit gotcha. I do it all the time. And unfortunately, the error message you're going to get when you do that is not going to say something as simple as you need to replace equals with tilde. It's going to say something like this: misplaced assignment. You may get some other odd error. So that's one of these things where you just want to pay very close attention to what's going on in your equations. But if you do it right, you should get a vector of type equation. And then we can assemble a system. So in Modeling Toolkit, there's so many different types of systems. If there's time involved, you're going to be most likely assembling an ODE system. But if there's no time involved, which is what we're doing right now, the steady state problem, then it's a nonlinear system. So we simply need to provide the equations, the variables, and the parameters that make up that system. Okay, and as you can see, we use the @named keyword, and that is doing a very simple thing, but a very nice thing. So basically, it's just making sure that the variable name and the assigned name are the same. So you can see that this is model NLSys. So that is exactly the same variable name we're using, right? Just a nice little trick that you get from these macros in Modeling Toolkit. So the next step is we want to run structural simplify. You're always going to want to run this step before you assemble a problem. And as was, I believe, discussed last time, you can also run the macro mtk build, which will do these 2 steps all in one step. But that didn't exist last time this was done. So let's go ahead and clean up that code. So we can actually just write @mtk build. And I like to show those 2 steps anyway, because what we're going to see here is that we got a system with 1 equation. And that can be a little bit confusing if you're just starting with Modeling Toolkit. Because as you can see, we clearly have 3 equations, right? So why did we get 1 equation? So the answer to that is that, as I said, this @mtk build does the 2 steps. It builds a system, and then it runs structural simplify. And structural simplify is going to take these equations, and it's going to do a bunch of mathematics to figure out how to simplify the system, right? How can you rearrange the math and eliminate any variables that don't actually need to be solved numerically? So it turned out that actually we only need to solve one equation and one unknown, which is actually the orifice area, the thing we're looking for, only needs to solve one numerically. Okay, so how do we solve that? So to solve it, we need to build a problem, and then we can go and finally run the solve function to solve the problem, okay? So the nonlinear problem step is where we can provide additional or information or change information about the defaults of the problem. So this is here to change any initial conditions, and this is here to change any parameters, okay? But these have all been defined previously when we set up our parameters and variables. So we can just leave them blank. We don't need them at this point. However, if we wanted to change it, then the way we would do that is, let's say we wanted to try for a different pressure. Here, let's change the source pressure. We could change that here by saying that's a parameter. So I'd say P underscore S is set to, let's say, 200 bar. So that's how you would go about using that feature. Okay, but right now we don't need to use that feature, so we assemble the problem and we go ahead and solve the problem. And we get a solution. However, you will notice that we see that the ret code explains that it's stalled. So this is another interesting change that we had from back in December. Previously, we didn't get this information. It just appeared that the problem solved without any issue. But now we have an issue, and it's stalled. So that means that it was likely doing iterations, and it reached a point where the iterations weren't getting any better. And so what we can do is take a look at how good is the solution, right? So this solution object is actually quite complex, and I'm going to talk quite a bit about what goes on in this solution object. So if we type sol dot and then tab, we can see what's inside of this object. And we can see that there's a res ID. So this is going to tell you the residual that the numeric solver was able to reach for each of the equations in the system. So we only have one equation that we're actually solving numerically, so that the vector just contains one value. And we can see it was able to solve with a residual of 3.7 e to the minus 10. So this is, now that we can see that, this is much less of a concern because this is a very small residual. And for our purposes here, this is completely acceptable, right? We don't need a solution that has, I don't remember exactly how many digits this is supposed to actually represent, but I can easily say that this is more than the number of digits that we need, which is probably 4 or 5 digits would be more than enough in this case. So why did it stall then? Though, because this is a very low residual. Well, the reason why is because the default tolerance is set to 1 e to the minus 10. So it almost got to 1 e to the minus 10, but it was just a hair short. So if we want to get rid of that error message or warning message, we can change our tolerance. So let's just set it to 1 e to the minus 9th. And if we run this again, then you can see that we get a successful solve. And now if we check the residual, we can see that it still went to 3 e to the minus 10, but it easily exceeded the residual or the tolerance that we asked for. Okay, very good. So what can we do with the solution object? So we can see that it contains a vector, but what is that related to when all these symbolic expressions that we have here, right? So we can index the solution using those symbolic terms. So this is one of the really powerful parts of Modeling Toolkit, is that we can use this symbolic indexing, which is just such a cool thing. So if I ask for, well, okay, we're after this orifice area, so what is the solution for it? We can get that solution just like that. But what if we wanted to get something else from the problem? So we can see that the solution only contains that one value. What if we wanted to know what was the velocity, right? Well, we can actually easily index that as well. And that's a really interesting thing because, as I noted before, this is actually not a symbolic variable. This is a symbolic expression. So that's actually what I did here. I actually asked for not just a single variable, I'm asking for an actual expression. And Modeling Toolkit is easily able to handle that kind of scenario using this symbolic indexing. So that's a very cool thing. So we're going to talk a bit more about the solution object when we go to the next level of fidelity, which we're now going to move to an actual dynamic problem. But before I do that, let me just see if there's any questions, open questions. Hopefully everybody's following along okay. Aha. So yes, someone is asking about the how do we type Unicode. So that is yet another really cool feature about this VS Code extension. And my apologies, I should have mentioned that. So when you type a variable, so let's just type my name, you can then do backslash and tab. Oh. Okay, why is that not working? Yeah, okay, sorry. So you need to start typing a LaTeX representation. So if I want to do X underscore something, I can start typing the LaTeX expression of that, right? And so that is when I finally see the menu. So as you can see, we get a subscript menu that is quite extensive. We have all the numbers. We have most of the alphabet there. And we also have some additional Unicode characters there. So if I wanted to do X dot, I could start typing dot, right? So it's the same as you would type in LaTeX essentially. And you then go ahead and get this menu. So it's just, you got to do backslash and then start typing something that you would find in LaTeX. So, and then if I hit tab, that'll actually give me the Unicode decoration of X with the actual dot above it. And to add on that, if you want to do double dot, that's DD dot. Okay, very good. Let's see. Okay, so there's a question. Since you're able to change parameters, can you change the parameter index by parameter? Yes. So as you can see up when I was building the nonlinear problem, you can symbolically change your parameters there, right? You don't have to index the pars. You just type the symbolic term. And as we move later into component-based systems, you can index using namespaces. And in the solution, this is going to be something that I may get wrong here, but we have the problem, and then I believe we have PS, which should represent the parameter space that we can index. Let's see if I can get this correct. So that's another way. So if you want to find out, okay, I have the solution, but what were the parameters that came with it? Because you might be doing like a Monte Carlo analysis and you have hundreds of solution objects and you want to be able to figure out which one goes with which answer, you can always drill down and figure out like all of the information that went to building that problem or that solution. Okay, very good. So hopefully that answered your question. And okay, so there's a question, is sol.u and sol index of u the same? So no. So the u that I have here, this expression, this is the symbolic expression. The sol.u is unrelated. Sol.u is just where the numeric information is stored. So that's the vector of the solution. So those two u's, they're the same name, but they're two very different things. Okay, hopefully that was clear. Oh, okay. So the question about the parameter index was, can you index parameter from the solution? So meaning, can you type P sub S here? And as you can see, the answer is no. And it actually explains that this is deprecated. Instead, you have to type this. Yeah. So that's for reasons that would be a deep dive discussion. But basically, what I did back in December and what I'm doing now is that Modeling Toolkit went from version 8 to version 9. And what happened in that change was a very large reworking of how parameters work. So parameters are much more complex now. And they are now, yeah, they have to be indexed in a different way for long story short. Okay, very good. So let's move on now to doing a higher level of fidelity with our problem. So yeah, so we were able to show that we could actually solve for that orifice area. I think it was something like 0.0009 or something like that. So that's cool. So now you have a pretty good idea of what you can do to solve this problem. But and maybe you present that to your manager and the manager's like, yeah, that's great, but are we sure that it's going to be at that target velocity even in the transient? So, let's hit this with the worst case scenario and let's see, does this orifice really work under all conditions? Okay, so to do that, basically that means that our x dot is no longer known, right? Now we need to solve for x dot. And so, okay, so let's turn it red and turn it into a variable that we're going to solve. And I write here, okay, we still have the same equation set. And we still have essentially 4 equations and 4 unknowns because x dot and x double dot and x are all just related as differentials. So that becomes more clear when we write down the actual code. So let's go ahead and bring in the code for solving this problem. So I'm going to copy and paste this. As I said, this will be the same code that was the exact same code that was done last December. And I'll go over some important details that have changed since that time. So one of the first things that you can see here is that the a time independent variable of time and a differential object need to be created. However, these are now provided by Modeling Toolkit. So we can actually get rid of these guys and say using Modeling Toolkit, T no units as T and D no units as D. So we can now, these are already predefined in Modeling Toolkit. We can just import them like this. this is going to be a boilerplate line of code that you're going to want to use for a majority of your models that you'll be creating. And as you can see from the name, these are going to be defined without units. And that also implies that Modeling Toolkit offers the ability to have units. And I think that would be a great next part of the series, is to go ahead and go through these problems with some units involved. But to keep this in a simpler, to simplify this, let's not involve units just yet. So everything here is going to be just assumed SI units, meters, seconds, and pascals for pressure. So it's all just SI units at the moment. Okay, very good. So we have that, and then we have pretty much the same two lines of code that we had before for the steady state, but you might notice a couple differences. So for one, X now involves, all the variables now involve an independent variable. And you also might note that we're specifying what that independent variable is. So there was a question previously about PDEs. Does Modeling Toolkit support PDEs? Yes, it does. And that's exactly why you do need to specify what the independent variable is when you're defining your variables. Because you could specify any set of independent variables that you'd like. So if you're doing a 2D PDE problem, then you might be specifying that this is a function of X and Y in time, right? So we're not going to get that complicated right now. We're just going to involve time. So that's what we have to specify here. And then, of course, the other thing you might notice that previously we're specifying pressure P1, P2, and we were solving for the orifice, but now we've swapped out the orifice for position. And we will have now 5 variables. And so we end up with 5 equations defined here, because we get these 2 equations from defining the differentials. So the derivative of x, of course, is x dot, and the derivative of x dot is x double dot. So here's where we find our balance, right? We've got our 5 variables, and we've got our vector of 5 equations. Whoops, let me make sure I define all this code. So I'm just doing Shift Enter, as you can see, to do line by line execution. And then now that is going to evaluate properly. Everything is defined. So these are the same equations we had before. We're simply just adding the dynamics, and we're just swapping around what we're solving for. So now that we know that the orifice ought to be this big from our steady state solution, we're going to use that now in our dynamic solution and just check. Is that correct? Do we always get that the x velocity, the actuator velocity, is limited to 1 meter per second? Okay, so now let's try to run the same code that we had before. And I can tell you part of why I wanted to do this is that I can show you that we're going to see something go wrong here. Or at least we're going to get a warning, and there it is. So as you can see, this warning says that the initialization system is overdetermined. And so this is one of the big points that I really wanted to show today, is that if you were working on Modeling Toolkit since the last year, some of the models that you generated a year ago are probably going to need to be updated if you're going to move to Modeling Toolkit v9. Otherwise, you're very likely going to start seeing this warning. And this warning is actually a very cool thing. What Modeling Toolkit can now do is actually assemble and solve an initial problem to solve for your initial variables, where previously it was a bit more on your shoulders to figure out what the initial values need to be. And that's exactly what I had done here, is that I had specified what all of the initial values should be, including calculating what the initial acceleration ought to be. So what I'm going to show now is that we actually don't need to do all that work anymore. We can make this problem a lot easier for us to deal with as engineers. So what I'm going to do is change this into a block of code, which is also something that is something that you can do. So you don't have to list everything in one line. You can easily put this into a block of code with a begin and end. And we can go ahead and just turn this into a much cleaner, much easier to read list of variables. And what I want to do is change this into okay, sorry. So what we see here is that these expressions, when you list a variable and say equals, Modeling Toolkit now interprets that as a initial equation, okay? And so before, the definition of exactly how this expression was interpreted was more of a guess. It was called a default value, is actually the terminology that was used, but it was treated more as a guess value. And now this is treated more as a initial equation. So that's a very big change that occurred for Modeling Toolkit. And so you have to be very careful when you're defining variables. If you're using equal sign, then you need to make sure that you're noting that, okay, that you're telling Modeling Toolkit, this is an actual equation. X has to start at 0. It's not allowed to be anything else at time 0. And that's exactly why we see here that the initialization system is overdetermined. It's saying we have essentially, it's overdetermined by 3 equations. Okay, so that is coming. I can tell you that's happening because of what we've done here. So we have 3 extra pieces of information that are over specifying this problem. And what those are basically up to us, right? So how do we want to initialize this problem? We can think of this more in an engineering point of view, like what do we want at time 0 for the system to be doing? And for our case, what we'd like to do is we want to just start the actuator at some position, and we want to start it at rest, right? So we'll just say the velocity is 0, and what we're going to do is start the system such that the source pressure is at 300 bar and the return pressure is at 0. But let's just say we don't know anything else. That's all we want to specify. So we can actually remove this information. So the chamber pressures, we don't know what they are at time 0. And the acceleration, we don't know what it is at time 0. We want Modeling Toolkit to actually figure out what that is for us. So instead of specifying an initial equation, we can specify a guess. And 90% of the time, it's okay to just give a guess of 0. And so that's what we'll do here, just to make life easy. It would have been also fine. I could have inserted that expression I had before here as well, but I'll just prove the case that you can just set your guess to 0. Okay, so I'm going to update my vars, and then let me go ahead and just do reevaluate everything here again. And now, when I assemble the problem, now Modeling Toolkit is happy. You can see the overdetermined system warning went away, and we can go ahead and now solve this problem. Okay, so let me go ahead and pause and see. I think we got some additional questions here. Question, is it possible to pass dictionary parameters, particularly for large-scale problems? Yes. A vector of pairs or a dictionary of those pairs is completely acceptable. Yes, so there's a comment about units. Yes, units would be really fantastic to be able to demonstrate that. So I'm gonna promise that one of the next parts of the series, we're gonna do one of these problems with units included. And then next question. Okay, so the question is how to specify your dependent variables if it's respect to time and space. I'm going to say that the best way to answer that question is you should go to methodoflines.jl, where PDE problems are, that's a tool that utilizes Modeling Toolkit. It's a kind of an extension to Modeling Toolkit to help you solve PDE problems. And there'll be lots of examples there to explain exactly how you should be specifying your dependent variables based on how you're setting up the problem. Sorry, I should be saying independent variables. Okay, and the last question here, is it possible to set a range for the variables? I'm guessing if you're talking about maybe for the initial guess, I don't believe you can set a range. And then if you're speaking in terms of constraints, yes, there's many different tools to be able to set constraints. And that's a very much depends. If you're trying to do an optimization problem, you can set constraints there, or you can set callbacks that can also enforce a constraint, I believe. Okay, so we're running. Oh wow, should have been paying more attention to time. We're running out of time. So let me go ahead and just quickly finish here and just plot some results and explain the solution object a little bit more. So if we go ahead and plot the exact data that we got from this solution object, which we can get from accessing the time and indexing, let's plot the position of the actuator. We can see that the solution looks like this. We actually just got, I think it's 6 points here, which is not a very smooth curve, right? And it's actually very interesting that we only got 6 points here. So what happened was the solver actually solved this problem adaptively and took the most efficient path it could under the tolerances that were specified. So for ODE problems, I believe the default tolerance is 1e to the minus 6 maybe for the absolute and the relative tolerances. So that's exactly what we get, is just these 6 points. And you might wonder, okay, but what if I wanted to see information in between those 6 points in time? So there's two different ways you can go about that. If you're plotting, simply use this expression instead of this expression. So basically there are recipes already defined for plots.jl, which work like this. So basically you just provide the solution object, and then you provide the symbolic indexes of what you'd like to plot. So that's what IDXS represents, is what are the symbolic indexes. So you could say X or X dot, for example, and you can see now we get this nice smooth curve because what you get from that solution object out of the box is built-in interpolation. So the other way that you can access that interpolation is to simply ask for a specific time. So if we say we want the solution at 1e to the minus 6, then we can get that. And that's already done the interpolation under the hood for you. And if we wanted it for a specific value, we can also specify the IDXS here. So if we wanted to know what X was at 1e to the minus 6, there you go. Okay, very good. So unfortunately, that is it for the time, but I will just give a quick talk about what was going to happen next. So the next level of fidelity that we're going to go to was to solve this as a compressible problem. And that means things get a lot more challenging. So the best way to solve this problem if it's compressible is to use components. And that's one of the very powerful features of Modeling Toolkit, is that it supports acausal component-based modeling. And so the way we would do this, we'd define a volume component. We'd define an actuator by combining the volume and the mass component together. And then we can go ahead and define our system like this. We created an actuator. We can create a orifice component, and we can create some source and some pressure boundary condition components and a damper here. And we can just connect it together like Legos. And that makes it a lot easier to build these problems, because the hardest part of dealing with compressible flow is the volume component, right? So we have to deal with how do we deal with changing density with a changing volume at the same time? Like it's a bit tricky, very numerically challenging to solve that. And if we can just define all that in one component, then we can let Modeling Toolkit do all the work for us of assembling all the equations. And yeah, so unfortunately, that's all the time that I have, but I will show real quick what that code looks like. And then we can just call it a day. And hopefully the next part in the series, we can dive a little bit deeper in how to do that. So let me just copy paste the code real quick, and I'll show you exactly how that would work, and give a quick teaser for what would come next. Yeah, so what we would do if we're going to do a component-based model, which, sorry, I've lost my place. Here it is. So let me just put it. So what we need to do component-based modeling is connectors. These define the domains. So we would have a hydraulic connector, and we would have a mechanical connector. Hydraulic would define pressure and flow. Mechanical would be velocity and force. There's a lot more to say there, but let me just keep it short and say that's just a necessary part of how all this works. So the rest of the work is simply just defining components that can be used and connected together. So an orifice would be defining that equation that we would that we've been discussing, right? So we can just put that equation here and define that as a simple component. And the parameters go in a parameter block, the variables go in a variable block, and we define ports that allow us to connect to that component. So that would go in the components block. And that is how you do it. So you define the physics, and then you wire up the variables of the component to the ports. Okay, so you do that same idea for each of the components. So there's an orifice component, there's a volume component, there's a mass component, and then you can assemble all those together to create an actuator. And then you simply create a system that connects all of that together using this connect statement. And it's as simple as that, right? So I think it would be really nice for the next series to go over all of this in detail, and to again continue to correct some of the errors that were or the changes that are needed to go from V8 to V9. But for now, because we're over time, I'll go ahead and just pause there and see if there's any final questions. Okay, yeah, I think that's it. And there was a question about if the recordings are available after the meeting, and the answer to that is yes. This should be available on YouTube in short order.
Yes, and also we will email you the link to the video, in a couple of days, so you can watch it at your convenience.
Perfect. Okay, great. Well, thank you so much for everyone for joining this webinar. I hope it was useful and helpful. And yeah, I hope that we continue the series, and help everybody learn how to use all this fantastic tools from Julia. Thanks, everybody.
Thank you for the wonderful session. And you can go to our website in the event section. and watch all the upcoming webinars. And we hope to see you in some of them as well. And in case you have any questions, you can write it to us and we will answer them shortly as soon as we receive them. All right. Thanks a lot. Thank you, everyone. And have a great day.
All right. Thank you. Bye.